Concrete is the main building material for different constructions. Therefore, it is very important to study the long-term process such as shrinkage, creeping, swelling, temperature impacts, and crack resistance that affects its strengths. Familiar methods and relevant laboratory studies incompletely describe the process of complex composition of materials such as concrete and masonry concrete.
Excuse me. Your screen is not sharing with us. I think you need to share this screen.
So,
Oh my God.
one moment.
So our presentation is not shared. Actually, we try to share our presentation from,
Yeah, we have 3 icons on the side. Yes.
Well, it wasn't visible before, but now it's all right, right?
Correct.
It is visible right now. Great. Okay. So we're going to full screen. So everything is all right now. Okay.
Yes, the screen.
So should we proceed? Thank you.
You can start.
Okay, the selection of experimental methods is quite important. We may select several basic methods. These are photoelasticity, Moir patterns, X-ray, and electronic microscopy, etc. Methods based on application of elastic waves, acoustic emission and impulsive ultrasound method, acoustic holography, tensometry method of mercury porometry, computational methods based on the study of different mathematical models. Holography allows us to study diffusely reflective surfaces interferometrically, compare the two wavefronts at different times and record the object on the photoplate in the initial state, and after acting on it, the image of object to be restored will be covered by interference strips, the configuration of which fully determines the change of the object. The part of the hologram that uses interference comparison of waves is called holographic interferometry. Obtaining holographic interferometry is performed by the following method. The first exposure on the holographic photographic plate registers the object in the initial state. Then, without moving the holographic photoplate, it is exposed for the second time, after the object undergoes deformation. A new one is then placed in the exposed film, and the holographic process continues. After proper photographic processing of the exposed photographic film, we obtain a holographic interferogram. The exposure time depends on the power of the laser and the type of photoplate. A holographic interferogram allows not only to reconstruct the front of a light wave scattered by the body at two different points in time, but also to observe their interference under ideal conditions. Through holographic interferogram, it is possible to obtain both a qualitative picture of the deformation as well as quantitative value of the vector of movement at any point in the body non-contactly. This is scheme of record of plate techniques. On this figure, a two-beam holographic recording scheme of late and techniques is shown. A laser beam is divided by divisor on two beams. One of these beams is a reference beam that is directed onto a photographic plate by means of a mirror. The second beam falls on the object, is reflected from it, and also is directed on the photographic plate. These two coherent beams meet in the plane of the photographic plate. Interference and interference pattern is recorded on the plate. The method of holographic interferometry is the best possible way to observe the early stage of the formation of concrete structure and study the process ongoing in the course of strengthening, which are not visually observed. It is used for scientific research to measure the deformations, as well as for monitoring and diagnostic of mechanisms made of different materials, as well as concrete and reinforced concrete structures. The suggested method is of utmost importance for monitoring of crack deformation, shrinkage in the early and different stages of observation without contact. This method is very important for the concrete quality monitoring in hydraulic construction of the concrete dams. Prior to the use and the application of various types of cement in hydraulic construction, it is necessary carrying out preliminary experimental study of the composition of the concrete, quality control and diagnostics of industrial methods, including non-contact, non-disturbing using a capacitive holographic interferometry method, such as shrinkage, cracking, and other processes on which the stability and durability of the building are further depends. Perception of shrinkage process in concrete structures and reflection of the dynamics of the stress-deformed condition allows us to observe concrete at an early stage of its structure formation by the method of holographic interferometry. The photo shows the interferograms of the entire observation cycle, cement matrix, and large fillings of 2 cm diameter granite in free condition. This is our photos, and it shows after 40 hours interferograms. The second one is after 62 hours, the third one is after 89 hours, and after 140 hours. No cracks were observed in the contact zone between the cement matrix and the granite stone. The granite stone moves along the matrix during the shrinkage process. This is granite plate, and this is a granite stone fixed rigidly. Interferograms of a cement matrix and granite stone fixed rigidly with diameter 2 cm fillers. This is also the photos, our interferograms. This first one is after 60 hours, second one is after 62 hours, second one 120 hours, and this. The stain deformed process grows in the contact zone of the matrix and the large filler. A crack was formed that was not visually marked on the sample. 62 hours later, a crack developed, indicated by an arrow. The strain deformed state increased in the lower zone of the specimen. After 120 hours, when the crack developed intensively, the strain deformed condition decreased. The crack was not visually observed, and after 489 hours, when the crack crossed the entire matrix, the crack was visually observed. Interferogram of the standard sample of concrete during bending. The sample undergo a breakdown in the early stages of the test, as is indicated by the arrows. The relative crack resistance of 3 types of cement was studied. Standard 6 samples with size 4 60 cm were made. The types and sequences of cements are given in the table. The specimens were placed in the sequence in 6 specially made 3-point bending devices, and all 6 specimens were placed in the rack with the specimen. The holography of the samples was done by the same method as in the previous experiments. 4 interferograms are given. This is a kind of cement. The first one is Portland cement, low heat output and low alkaline cement. Second one is a Portland cement, and etc. This is the loading devices and the rack with the specimen. And these are interferograms of the specimen 2 hours after loading. The number of the same as they correspond to the number of the cement type in the tables. This is an interferogram of the specimen 14 hours after the loading. Third one is after 80 hours and the fourth one is after 20 hours. And the first cement in our table turned out to be most cracking. Development of the methodology of current processes in concrete. Shrinkage is a long-term process, so we were faced with the task of creating conditions in which it would be possible to observe the development of deformations in the early stages of handling. 10-30 hours after the preparation of samples, contactly shrinkage. Other methods available do not allow conducting these experiments. For the durability of concrete structures, the process of forming the structure is crucial. Concrete specimens for the experiments were prepared in the Hydraulic Engineering Laboratory of GTU, Faculty of Construction, consisting of a diameter 150 mm metal disc. It was 20 mm, and the granite cylinder diameter is 10 mm, and height 20 mm was inserted in the middle of the cement matrix and inserted into the port. The sample was stored for 10 hours in the humid environment at 200 Celsius plus minus 20 Celsius ratio. Two types of cement were used. Portland cement B22.5 and second one is B13. After 10 hours, the samples were removed from the humid environment and fixed on a holographic stand in a two-exposure diagram. This is a cement stone samples. On the left side is B22.5 and right side is B13. A is metal cylinder, B is a cement stone, and C is larger filler. 1, 2, 3 is the measurement points, what we have measured. A continuous cycle of recording and observing holographic interferograms was 20 hours. Sample age was 10 hours, and total it was 30 hours. After the first exposure, which is a 50 second, an image of the sample was observed on the holographic plate. The second exposure was performed on the same plate after 1 hour. The duration of the exposure was 50 seconds, after which the two exposure plate was removed from the cassette. These are the samples. First sample is Portland cement B22.5. Sample age is 11 hours and exposure duration is 50 seconds. Time between exposures was 1 hour. This is second one. This is Portland cement B22.5 also. Sample age was 30 hours and the exposure time also was 1 hour. This is second sample age, which is Portland cement also, but this is a B30, and the exposure duration was 50 seconds and time between exposures 1 hour. This is geometric scheme for calculating deformations. One is an object, two is a hologram, and ABC observation positions. Formula for calculating numerical data acceptable deformations. This is formula for the calculating numerical data of acceptable deformations. Calculating the numerical data from the interferograms gives the integral curves of the movement of individual 1 to 3 points along the x-axis in the cement stone. 10 hours to 30 hours from the solidification of the cement stone, where the major filler is the granite stem. After processing the data obtained experimentally, the displacement of the point 1 in the B.22.9. Portland cement at 30 hours is 8 micrometers less than in the B30 sample. the displacement of point 2 is 10 micrometers less, while the displacement of point 3 is 11 micrometers less. We determine the number of interference fringes by means of special collimator. Holographic interferometry enables us to evaluate qualitatively and quantitatively the stress-deformed state of a concrete and the process of shrinkage, crack formation, and development of concrete of different compositions. The advantages of this method can be considered as the following: high accuracy, tenths of the wavelength of is 633 nanometer equals 63 nanometers, which is a nanotechnological research method. Large amount of information received, ability to study real materials and goods, no contact with the study object, no contact method. The new phase begins with the development of this method that implies the improvement and development of research methods, as well as broad introduction of its result in practice, which will further facilitate the reliability and durability of concrete and reinforce concrete structures, one of the major building materials in construction, in particular in hydrotechnical construction. This will create a solid foundation for engineering technical personnel working in this field. This is our this is our university, Georgian Technical University Faculty of Civil Engineering, Holographic Interferometry School and Scientific Research Laboratory, and this is our laboratory. This is an optical setup for interferogram recording, helium-neon laser, and this is used for experiments. This work was supported by Shota Rustaveli National Science Foundation of Georgia, grant number FR 8011-671, investigation of concrete deformation by holographic interferometry method. Thank you for your attention.
Hi, thank you for the presentation. And now you're open for questions.
Discussing. No questions. Thank you very much.
Thank you.
Thanks a lot.
Oh, it's so hot.
Any questions? Anyone have any questions?
Wow. So we will leave you, and thank you very much for your attention.
Thank you, Georgian team. You can, in the meanwhile, join other sessions if you want to listen to them.
High-density silicon photonic integrated circuits. In the last 2 decades, there has been a game-changing transformation of integrated microphotonics. Silicon has become the material of choice to fabricate photonic integrated circuits whose complexity is increasing according to Moore's law. In addition, in the recent year, the development of open access technology platforms for manufacturing medium volumes of photonic integrated circuit using highly standardized waveguiding structure, building block and design layout tools has strengthened. Since those processes are based on multi-project wafer approach, the cost per unit area of peak is gradually decreasing, making them attractive for several cost-sensitive application domains, including point-of-care testing. Here in the slide, you can see the market forecast for silicon photonics. You can see that immunoassay tests in blue is a high growing rate market for silicon photonics. And in this part of the slide, in the right part of the slide, you can see Himax fully integrated silicon photonics platforms comprising low-loss waveguide devices, FP fiber input-output, and modulators and detectors. Despite the remarkable achievement, photonic integrated circuit on silicon insulator substrates have some important limitations, including the high birefringence, typically larger than 0.5 of silicon wires commonly used to guide light within these circuits. In fact, silicon photonics components are typically designed assuming that the propagating mode is either quasi-TE or quasi-TM. In particular, in the field of biosensing, by far the most used mode is the quasi-TM mode, since it has a lower confinement factor in the silicon wire than the quasi-TE mode, and consequently a more intense evanescent field. Thus, TM-pass polarizers are becoming essential components for the development of silicon photonic biosensing applications, and research efforts on them are quickly intensifying. The slide shows the birefringence of silicon nanophotonic waveguide. We can see that the two fundamental quasi-TE and quasi-TM mode have a very different effective refractive index, and this is shown also on the mode distribution of both the modes. So this slide shows the reason why we need polarizers in the context of silicon photonics. Several silicon insulator TM-pass polarizers have been proposed and experimentally demonstrated in literature. The following slide shows several approaches for TM-pass polarizer. Here we can see an approach based on one-dimensional photonic crystal. In this approach, we can see a grating, a one-dimensional photonic crystal. The structure allows TMO to pass through the structure, the yellow arrows, while the TE mode is reflected. The length of this device is extremely short. The insertion loss is only 1 dB. The extinction ratio is very good, 34 dB, and the bandwidth is approximately 200 nanometers. An alternative approach is based on a two-dimensional photonic crystal. In this case, we have a line defect in a two-dimensional photonic crystal, having a length of approximately 5 micron. Again, the structure allows to TM mode to pass through while the T mode is reflected. The insertion loss of such component is extremely high, 45 dBm. The insertion loss is quite high for the device on the left, while the device on the right has an insertion loss of only 0.6 dB. Another approach is based on a TM-pass polarizer. So we have a silicon strip waveguide embedding a graphene silicon nitride graphene multilayer. So in this way, I have a very large loss for the TM mode, while the TM mode suffers from a very low propagation mode, and in this way we obtain an insertion loss less than 3 dB and an extinction ratio larger than 40. This slide shows a class of devices which are photonic plasmonic hybrid grating waveguides. Here we can see a periodic structure in which I have an hybrid structure, plasmonic and photonic, and this structure is designed so that the TE mode is rejected and the TM mode pass through with very low loss. The record insertion loss is obtained for the device on the left with an insertion loss of only 0.1 dB and a length of 2.5 micron. The extinction ratio is not so high, 26 dB. Here we can see a silicon wire coupled to a highly doped silicon waveguide. In this way, I have again a high propagation loss for the TM mode and a very low propagation loss for the TM mode. So the insertion loss of the device is 3. The extinction ratio is 30 dB. This is a very complex device to be fabricated. This is based on a silicon wire with a vanadium dioxide film on the vertical side walls. In this case, the vanadium dioxide in the electric state is represented in purple and the metallic state in gray. In this last situation, metallic state of vanadium dioxide, we have the propagation of only the TM mode. An alternative approach to obtain an efficient TM-pass polarizer is to use sub-wavelength grating waveguides that are designed to reject DTE polarization. The insertion loss of such devices range from 0.2 to 0.7 dB. The extinction ratio may be larger than 40 dB for the second device in this state. This is a very interesting device. It is a waveguiding structure with two tapered waveguides sandwiching a narrow waveguide only supporting the TM propagating mode. The insertion loss is low, 0.2 dB, and the extinction ratio is 26 dB. This is the same concept that we already saw. We have a waveguide with highly doped region close to the waveguide core, and in this way I suppress the TE mode and allow the propagation of the TM mode. We propose a TM pass polarizer in silicon insulator technology that is designed taking into account all the above mentioned requirements in terms of the easiness of manufacturing, a very low insertion loss, and high extinction ratio. Aiming at being compliant with all the open access multi-project wafer silicon insulator-based processes all over the world, the design assumes the standard silicon insulator wafer with the top silicon layer having a thickness of 0.22 micron and a minimum picture size of 0.15 micron and a minimum picture spacing of 0.1 micron. In addition, the designed polarizer can be manufactured in a single lithographic step and exhibit large fabrication tolerance. The components exhibit a record insertion loss of 0.05 dB at 1.55 micron, a high insertion loss of 36 dB, and a broadband operation with insertion loss less than 1.6 dB and extinction ratio larger than 30 dB over 200 nanometers, covering SC and L bands. The proposed TM pass polarizer includes two device sections with length L1 and L2. The first device section is the covered directional coupler, which allows coupling between the fundamental quasi-TM mode of the input strip waveguide and the slot waveguide. Both these waveguides support only the fundamental quasi-T and quasi-TM modes. Through appropriate phase matching, the TM0 mode of the strip waveguide can be selectively coupled to the TM0 mode of the asymmetric slot waveguide, while maintaining a high phase mismatch between the TE0 mode and of both waveguides. This inhibits coupling of the TE0 mode of the input strip waveguide to the TE0 mode of the slot waveguide. The second device section allows the slot waveguide to evolve in a strip waveguide, such as the power related to the input TM mode can be obtained in the output strip waveguide. In addition, the tapering of the input strip waveguide in the second device section eliminates the reflection of the input T mode. So, at the input of the device, I have the T and the TM mode, while at the output of the device, I have only the TM mode with a very low fraction of the TE mode that is reflective, is back reflective towards the input. These are the design curves. We designed the component aiming to obtain phase matching for the TM mode and phase mismatch for the T mode. And the table shows the sizes of the device after the optimization process. So these are the achieved performance. This is the 3D FDTM simulations of the device. We can see here that the input field is very well coupled to the output waveguide, while the T mode is rejected. So the insertion loss is extremely low, down to 0.05 dB, while the extinction ratio is 36 dB in the C band and is very low also in S and L band. We carried out also an analysis of the fabrication tolerances. The worst case value of the extinction ratio is of the order of 36 dB, while the insertion loss is always less than 0.3 dB. Moving to the conclusions, TM-Pass polarizer are becoming essential components for the development of silicon photonics biosensing application. For the devices in literature, the achieved extinction ratio are very good, with the record exceeding 45 dB, while the insertion loss is typically not very low, with values less than 0.5 dB only for a few devices. A TM-Pass polarizer intended for silicon photonic integrated circuit with a large component density is proposed. The design strategy is focused on minimization of the component insertion loss without degrading the other T parameters, quantifying the device performance, the extinction ratio band in the line. Due to its unique features, especially in terms of ultra-low loss, high extinction ratio, and ease of fabrication, the silicon insulator TM-Pass polarizer can be widely applied in ultra-dense high-performance photonic integrated circuit, especially those intended for the emerging field of silicon photonic biosensors. Thank you very much for your attention. Obviously, I can reply to all your questions if necessary. Do you have any question? Can you hear me?
Yes, we are here.
Okay, thank you very much.
I think we have a question. Mara Lucia, do you want to make a question for Francesco?
No, only to thank you for the presentation.
Thank you very much.
Any more questions? Thank you very much, Francesco.
Thank you again.
Good morning, everyone. It is my pleasure to present our research work to you. Today I will talk about this indium arsenide, indium phosphide quantum dot multi-wavelength laser and their application in terabit networking system. My name is Jingguo Lü. I put my co-author name here. We all work at the National Research Council Canada in Ottawa. Here I just show you outline of my talk. First, I talk about motivation of our research work, and then talk about why we choose quantum dot. I will give some comparison results between quantum dot and the quantum wave lasers. Then show you this what look like for quantum dot multi-wavelength lasers. We have done this optical and electrical design in the package for quantum dot multi-wavelength laser. For terabit networking system, for laser requirement, usually we need a very low relative intensity noise. Also, we need a ultra nano optical line width. I will show you some results for our quantum dot multi-wavelength laser in terms of noise performance. Then I will show you some experimental results of PAM4 in the 16 quant. Finally, give a summary of my talk. Here, just show you this one coherence architecture, networking architecture. And basically, in the transmitter side, we need many individual lasers to code the data on each laser. Then we mux together, then go to long distance. And then on the receiver side, we demux. Then we use a coherence detector to decode the data. When you use a coherence detector, we need a local oscillator to, that means we need so many lasers. This research purpose, we try to use just one laser chips to replace many individual lasers in the transmitter side, also in the receiver side. Then we can simplify networking system. Also, we can reduce cost. And that is motivation for this research work. Why we use quantum dot? In 1982, as the first time, Professor Arakawa in Tokyo University has proposed the concept of quantum dot. And National Research Council Canada has worked on the quantum dot semiconductor material since 1994 until today. And people already demonstrate many advantages as compared with BAT and the quantum wave-based semiconductor gate material. And here I just list some of advantages. For example, they have smaller lasing threshold current, better temperature stability, better back reflection insensitive. For multi-wavelength laser, very important is because the quantum dot gate material is highly inhomogeneous gate material, then we can achieve independent multi-wavelength operation. Here, just show you what quantum dot looks like. That is a plan view SEM of surface quantum dot. This is a quantum dash. Here, show you is a cross-section SEM imaging of a cone region of one quantum dot DIB laser. Yeah, we make it at the NRC. You can see here, this is grating. This is a dot layer. We have five layers. This is dot. Here show you that's a spectral PL intensity with a wavelength. We are using in the arsenide quantum dot or dash grow on the indium phosphide substrate. By controlling a grow condition, we can choose grow dot or the dash. Also, through quantum dot capping procedure, we can fine tune this emission peak wavelength, also 3 dB bandwidth. This slide I just want to show you comparison result between quantum wave and the quantum dot Farber-Borer laser with identical structure. And basically, we design, glue, and fabricate quantum dot Farber-Borer laser and the quantum wave Farber-Borer laser. Use the same laser mask, same doping, everything same, and then we compare their performance. This is quantum wave spectral. This is quantum dot spectral. In terms of flatness, quantum dot spectral is much flatter than quantum wave. And if we go whole channel, go to a high-speed detector, look at this RF beating signal, For quantum wave RF signal, which is very broad, unstable, they change time by time. But if your quantum dot spectrum go to high-speed detector, basically you only get one signal. It's very stable. They don't move. What that means? That means the quantum dot Farber-Bourou laser is a model-locking laser, but the quantum wave Farber-Bourou laser is not a model-locking laser. Then we also we look at the noise performance. This is relative intensity noise spectrum for quantum wave single line. This is for quantum dot single line. If we do integration, we can see here for quantum dot single line, average rate is minus 130 dB per hertz. But for quantum wave single line, it's minus 115 dB per hertz. That means the quantum dot single line is much better than quantum wave single line. Then we also use a hydroradar interferometer to look at this optical phase noise. For quantum dot single line, usually is less than 5 megahertz. For quantum dot single line, is larger than 100 megahertz. For this experiment result, very clear, quantum dot is much quieter than quantum wave lasers. Here, just show you more realistic indium arsenide quantum indium phosphide quantum dot-based multi-wave laser. This laser structure is very simple. This is Farber-Bourou laser. It's a rate waveguide. We also do Barrett laser waveguide laser. And on the both facets, sometimes we make a coating, sometimes we only make one coating. Depend the what kind of laser we need. Also gain performance. Here show you is a detailed layer structure. We do package it by ourselves in the butterfly package in-house. That's how we package it by ourselves. Here just show you some typical performance of our quantum dot multi-wave laser. That is optic spectrum. Because it's model-locking laser, we use optical autocorrelator. You can see nice pulse stream. Here is a time period is 20 picosecond, which is corresponding to 50 gigahertz quantum dot model-locking laser. Here is the output power with injection current. You can see laser swirl current is about 23 milliamp at room temperature. And also we did measure this pulse duration is about 300 femtoseconds. By using our quantum dot gate material, we can make a quantum dot multi-wave laser. This is C-band, L-band. For repetition rate, we can make it for 10 gigahertz, go up to 1000 gigahertz. We also do this optical and mechanical design and assembling. This is optical design. Basically, this is laser chips. Then go to a colorimeter, go to a beam splitter and an isolator, and then we go to fiber. And for this facet, go to a single mode fiber, the coupling loss about 2.4 dB. That is a mechanical design. This is a far field beam profile. This is for rich waveguide. If we use a high Barrett waveguide, which is much circle, it's like circle. We also do electrical hardware design and control. Basically, we have this use Athlon, have a fast feedback loop system to lock this output power and also absolute wavelengths. After we put this feedback system on, and we can our module, if you put it in the lab, run like 1 or 2 months, we can guarantee this frequency spacing is within plus minus 100 ppm. Absolute wavelengths stay plus minus 0.01 nanometer. We do this package everything together, and that is microprocessing, like analog interface board. This is optical block, which is quantum dot laser inside this power supply. We make this bench top together, and we have successfully delivered many fully packaged quantum dot multi-wave module to our industrial client, Ciena. Ciena is a local company, it's an international company, US company, but in the Ottawa, they have over 4,000 employees in Ottawa. We work with Ciena. We deliver many quantum dot multi-wave laser for them. Now I just want to show you one device which uses 34 gigahertz quantum dot multi-wave laser to run some terabit networking experiment. And this is laser structure, and basically rich waveguide. Rich wave is 2 micrometer, and this is detailed information for this device, for this material. This is LIV curve for this device. And before we use this laser for networking experiment, we need to investigate their noise performance. Also look at the optical spectrum. This is optic spectrum just for one laser. You can see here is the 6 dB comm bandwidth is about 13.05 nanometer, and which is provide over 48 channel with optical signal to noise ratio more than 40 dB at this operation condition. And that means use one laser, we can replace 48 traditional DFB lasers. Then we look at the RF beating signal, just go whole spectrum, go to high-speed detector. Then you can see here, RF beating signal is really nano. It's about 1 kilohertz. Yeah, that's line width is 1.68 kilohertz, and the corresponding time jet is 4 femtosecond. Then we also look at this relative intensity noise, is ring spectrum. You can see here for individual channel, for whole laser. Then we also look at this noise performance, optical line phase noise. That is for different channels, optical phase noise usually is below 2 megahertz. That is phase noise spectrum. Then we use this one integrator, we can calculate this phase noise. Then use this laser, we run experiment. We have quantum dot laser, we have isolator, optical filter, and then we just use one by one to look at each channel. Then go to this Mach-Zehnder modulator. We have a Arduino waveform generator, and then we look at this use optical monitor analyzer to look at the eye diagram. This is for data center application, and basically you can see back to back, with very clear eye diagram, PAM4 eye diagram. After 25 kilometers single motor fiber, we still see very clear eye diagram. That means we just use one laser. We have demonstrated 5.4 terabit PAM4 transmission capacity. And basically, total is PAM4, 48 channel times 28 gigabaud. That is the base rate. Then we have 2 polarization. Then we get a 5.4 terabit per second. Now I would like to show you another device, which is 25 gigahertz quantum dot multi-wave laser. That is LIV curve. You look at this optic and this RF beating signal. This is optical spectrum. You go to high-speed detector, you can see this RF beating signal with really nano, and that means this laser is a model lock laser, is really stable. Stay there. For this device, and the 3 dB bandwidth is 11.2 nanometer, which means provide over 56 channels with a signal to noise ratio more than 40 dB. So we use one laser, we can replace the 56 traditional semiconductor lasers. And before we run experiment, a terabit networking system, we still need to look at the phase noise and the intensity noise. Here is to show you the intensity noise. This is whole laser. That is one channel. For whole laser, which is really, really low, is minus 165 dB per hertz, which a traditional quantum wave laser uses minus 140 dB per hertz. And that means the quantum dot laser is much quieter than traditional quantum wave lasers. And even for each channel, still is pretty good. It's minus 131 dB per hertz. We believe is good enough for our terabit networking experiment. Then we also look at the optical phase noise. And that is a spectrum that we look at the 46 channel one by one to look at the phase noise. And looks at phase noise for this device is a little high for 1 megahertz up to 5 megahertz. And because we know if you want to run a coherent communication, we need to make sure this phase noise is lower than 500 kilohertz. Then we have developed one technology we call this fast feedback loop system. We use this fast feedback loop feedback locking system, and then we can reduce this phase noise for each individual channels. That is the result. For rate curve, which is free run, and the phase noise is for 1 megahertz to up to 5 megahertz. After we use a fast feedback locking system, then we can reduce phase noise at the same time for all channels, go down to 62 kilohertz to 346 kilohertz. That means all these channels, the optical phase noise is below 500 kilohertz. We also look at this RF beating signal. You can see here, free run, about 10 kilohertz. After use a fast feedback locking system, they reduce less than 1 kilohertz. Also, temperature also is about 1 femtosecond. Before it's about 10 femtosecond. Okay, then we use this laser to run experiment. This is for coherent communication. And before we show you that the result is PAM4 for data center application, here we do is 16 quant. And that is laser, same setup, but Mach zeta modulator we make change. Also, this modulation format is different. Then you can see here all is for different channel and back to back and over 100 kilometer single mode fiber. We still see very clear constellation diagram. And that means use our laser, we have demonstrated 10.3 terabit per second, 16 quant transmission capacity. And basically, we just need one laser. We can carry 10.3 terabit per second data bandwidth. Okay, summary of my talk. I have shown this in the slide in the fast-byte quantum dot material growth and the laser design, and presented competitive result between quantum well and the quantum dot based Farber-Bourlot laser. Also present basic performance of a different quantum dot multi-wave laser and the package modules. By using one laser, which is 34.2 gigahertz quantum dot multi-wave laser, we have successfully demonstrated 5.4 terabit per second and PAM4 transmission bandwidth for data center application, which also back-to-back and over 25 kilometer single mode fiber. And we also, by using one 25 gigahertz quantum dot multi-wave laser, we have a successful demonstrated 10.3 terabit per second coherent transmission capacity for coherent communication system. Yeah, here and last slide, I just want to show you that is our team. And I put a name here. Basically, this is a teamwork. A lot of people work on this project. And in the 2018, we achieved a big award for called Outstanding Achievement Award for whole NRC. NRC, we have over 4,000 employees across the whole country. Thank you.
Thank you, Professor, for talking. And someone has any question?
Yeah, if you have any question, you can send an email to me. I will reply you back to you with my answers. Okay, if no more questions, then thank you, everyone. Just go back stage, right?
Yes, thank you, Professor.
The electron, the size of this particle is not the electron itself, not the ball with the size of the classical electron, but is but is a spread of the wave packet. Okay, simply where you can find the electron by repeating the measurement. If there was a repetitive measurement on the single quantum state, that you would measure within the width of the wave packet. Okay, so let me now go. Okay, here is the classical stability diagram. These are the coefficients of the two-dimensional harmonic oscillator, which is strange because one of the frequencies is negative, so it's actually a saddle point. And this saddle point, of course, if you want to stabilize the particle, it must rotate. The saddle point must rotate, like in case of Paul trap, to achieve stabilization. So the next. Okay, let me now, so this was the original research. Now let me go to complexity, and in some 21, Irving Langmuir was trying to quantize helium atom and to quantize atom with 2 electrons, and of course the electrons are put on 2 circles now, like in case of the Bohr atom, and these circles are parallel, and you can say that 1 electron would be if you put a circularly polarized field, 1 electron would be in a Trojan wave packet state on one trajectory, and second on the other one. Okay, so let's explain these trajectories more. So I call them Hooper-Rings configuration because they correspond to the Hooper-Rings, and the first impression is that these considerations, these early considerations, are not very known and popular, so they are not showing up in handbooks. So okay, so now you can solve this. You can find the equations for the radius, and you will find out that the angle is always 30 degrees. If you draw the angle nucleus electron, the angle does not depend on frequency, on anything. It cancels, and it is 30 degrees if the nuclear charge is 2. Okay. So now we added, we wanted to stabilize it because without any fields the problem is unstable. So we wanted to stabilize. So this is my physical review letter with David Farrelly from Utah State University, and from 2005 when we added a magnetic field and a circularly polarized electric field, and here is magnetic field is perpendicular to the plane of motion, and the electric field is again in plane. Okay, the field is rotating here, and the plane is the B field is in this direction, and you can find out that classical trajectories can be stabilized, which are otherwise unstable. Here is classical stability analysis known. It's extended to rotating frame. Normally in handbooks of classical mechanics like Goldstein, it's done without rotation, but the rotation is more complicated because the stability matrix is getting and in the presence of the magnetic field, which the paramagnetic term looks like rotation. Also, there are terms showing up. So the next, okay, here what happens if you slightly make small perturbation without any field, so that there is some drift and there is no oscillations. And okay, so the most interesting is the stability islands as a function of the frequency of the circularly polarized field, and cyclotron frequency, which in this unit is either -1 or +1 because the frequency of rotation is related to this. So, and this is the strength of the field. So you get either classical, some funny shapes. The black is stable, white is unstable, and you can generate this. This looks like some night. Okay. And now, okay, then we can do quantum diffusion Monte Carlo simulations on that, which is propagating basically ensemble of walkers. Theoretically, mathematically, these are exact solutions of the Schrödinger equations, and you simply represent the wave function itself, not the probability density, but the wave function itself by the ensemble of walkers, and this ensemble of walkers is diffusing according to the Brownian motion. On short scale, on large scale, it's a Gaussian noise. So you can see that you can make quantum simulations exactly of these packets, because quantum Monte Carlo can do, unlike the Greek problems, it can do any number, inclusive of any number of particles, because it's probing. Okay, you can this I will skip, this I will skip, this I will skip. You can extend this concept of Langmuir trajectories to n electrons, and here is the example of 2n electrons, because if you have if you have odd number of electrons, then it's you cannot separate into two in analogy to original Langmuir. So if it's 2n, you can make the configurations like that. It's the result is n-gonal prism. Okay, and that here is the nucleus. You must tune the value of the nucleus now. So you can handle it with Hartree simulations. These are time-dependent Hartree simulations in Hartree limits, so there is no exchange, neither correlation terms. It's only Coulomb. You solve the Schrödinger equation for one electron in the presence of the Coulomb field of all the other electrons. Okay, and you can make the simulations of those using this method, because the Greek methods still is difficult to do Greek methods above 4 dimensions. 4 dimensions I think 6 dimensions now with the fastest, the biggest supercomputers are doable exactly, but if there is like 12 electrons, it's difficult. Now, let me go further. Okay, you can do also quantum diffusion Monte Carlo simulations. Here is the picture. Also, walkers are diffusing, and you get the original symmetry of Angonal crisp. So this is extensions of the. I want to underline that these configurations are stationary in the rotating frame. This is like a fixed molecule, and there are pictures of the probability density of electrons in chemistry of a molecule. That this whole thing is fixing. It is only rotating in the laboratory frame. When you add the electric field, it is deformed, so the symmetry is lost. So, but the box shape is for fields not so strong. The box shape is the same, but the only the basic symmetries are lost. Okay. Now let me go to the point. What we want to do, we want to somehow do something which is beyond the configurations which are stationary in the rotating frame. So this is another page from the Langmuir's paper. It is these are trajectories which are also somehow forgotten. There is no one is talking about them in handbooks, and also in the terms of quantization of helium, and they give really pretty good energies of helium. And the reason is because if you do two-dimensional simulations of helium, and you will find out, I don't have a picture here, but this is Joe Eberly, my supervisor, and Rainer Grober from Illinois State. They were doing a lot of publications on that, and you will find out there is a butterfly shape on a ground state with the repulsion when the electron coordinates are equal. So there is a valley there, and the trajectories correspond to this. They are augmented with the symmetry of this butterfly. Okay, there is I will explain them in details later more. Okay, so this is a picture of this trajectory. So what happens is that the electrons are no longer rotating, but they are oscillating back and forth. Okay, back and forth on a semicircular trajectories. One electron here and second electron here. So they are bouncing from each other periodically in time. Okay, and here is they correspond to very funny thing, which is the toy, which is called click-clack balls. You know that if you have, most of people know this toy probably because kids are playing it, and these are two balls which you put into motion with oscillations here, okay, with hand, and then the name is source. The name is from the sound, of course, no, and so they are moving back and forth on also semicircles. Now, here is the classical simulations of them. If you guess the equilibrium of forces for circular trajectories, simply that the repulsion between electrons plus attraction to the nucleus is equal to the centrifugal force. So this guess leads to this kind of trajectories which are excited of those Langmuir was considering. And the next picture. Okay, here what happens if you excite them more, if you make the same excitation as before, but also make some perturbation in z direction of the planar motion. So you get some funny shapes which resemble plasma in fusion devices. If you look at there, it has something from hot fusion. Then, okay, so if you by hand adjust the initial condition by a few percent, you will get the Langmuir trajectories as this simulation over about 100 of periods, and then okay. And so what we have is now that we have simple hard wall theory, which is we approximate the semicircles by perfect circles, and we approximate the bouncing, the click-clack balls bouncing between electrons as between hard balls, which we impose on single electrons into the wall. And you know that if the electron, if the collision with the wall is perfect, then the trajectory will remain perfect circle, perfect semicircle. Okay, because the Langmuir trajectories are not perfect semicircles; they are altered. We also decompose the linearly polarized field, which is put along the symmetry of the Langmuir trajectories and into two CP fields, and each CP field is coupling then to the electron in the right rotation direction, which allows to assume that the electron is in a lot of time in the Trojan wave packet state, and then only deviation is here when there is as you know, if you make simulations of wave packet bouncing from the wall, it will reshape. It will reshape to the Gaussian wave packet back. It will not be damaged. So this is the basic model. So here, far from the bouncing, is mainly Trojan dynamics, and here is collisional reshaping. And this way we can apply the theory of the Trojan wave packets basically to each of the electrons, because of course you can apply symmetrically the same theory here when you can put wall here, and we can apply the theory here. So this way we can rescale our all results before, which are for Trojan wave packets in a circularly polarized field, and for Trojan wave packets in both the circularly polarized field and the magnetic field. We can rescale and we can guess the approximate stability of the trajectories that way, because otherwise there are only simulations possible, and classical simulations, and some Rick Heller wave packet time-dependent wave packets with time-dependent parameters method. It's all numerical, but the theory we have this. We can rescale then all the theories, both the harmonic and the Mathieu theories onto one of each of the electrons, and to find out for which fields the trajectories are stable. So let me go further. I think it's time soon ending. So let me show you the volumetric plot here again of the packet that of one of the electron packets. So this is the volumetric cross section. The packet is cut into half, so you can see inside. So this is the highest density. This is the lowest. To the red goes to lowest density, probability density. So this electron moves like that, and the second electron moves like that. The second electron is mirror symmetric. Okay. So let me go. So I think it's time to summarize, because it's I have 5:26 now. So in 21, Irving Langmuir, in early attempts of the quantization of helium atom by Bohr-Sommerfeld conditions, found that the periodic planar to semi circular like two electron classical trajectories The trajectories correspond qualitatively to the popular toy, the click-clack balls, when the electron nucleus Coulomb potential is equivalent to the Boltzmann joining string and the Coulomb periodic collisions by the hard ball collision. The external oscillating field in the directional symmetry axis of the trajectories configuration, and while the motion perpendicular magnetic field is caused the rotation of the configuration. So you have you can induce precession of the whole shape with the perpendicular field. When the plane of the field is also rotating with the half of the cyclotron frequency, so you must superpose now the linearly polarized field from two circularly polarized fields with slightly different frequencies now. So to obtain the rotation of the polarization. Such trajectories can support the stable non-dispersive two-electron quantum wave packets with the probability density solitons moving along the trajectories with some shape oscillations. There is a main difference that in the previous cases the probability shapes are all frozen, but here there are some oscillations in shape because of the recollision, and they can be confirmed in Hartree for three-dimensional Greek simulations in the Hartree limit as well as within the stationary and our recently developed new time-dependent quantum diffusion Monte Carlo method. I developed recently new quantum Monte Carlo method, which is not popular till now. No, it's not used at all. It's a new method when you simply extend walkers to many kind of properties. So walkers have properties and they can be annihilated. And okay, here I would then stop.
Hi, everyone. Thank you for the great talk, Professor. And I would like to open for questions. If someone has questions, please put in our private icon or enter on the stage. I think no questions. Thank you so much.
Okay.
My screen, go here. All right. Thank you very much for your patience. This is Denis Gendron again, presenting you about quantum oil refining as a viable path to meet the Paris target. So what we're finding out is that as depletion, the oil depletion is rolling out, we're facing two possibilities, okay? Either to compete for limited resource, a bit like kids fighting for toys, or to team up in the real battle against solving a common problem. If we choose the first choice, you know, we're going to end up at two, but when we do, we'll be more divided, older, have less time to solve problems such as greenhouse gas with less resources and a greater state of panic. But if we choose two, things will get better as quickly as possible. Our global economy, they still depend on hydrocarbon for energy and polymer material. Solving these problems, increase energy efficiency, carbon neutral energy source, improve battery, and new scalable energy storage will reduce our use of hydrocarbon. And this is essentially what we're talking about here. So the choice two is the best choice, okay? And only if we they go in that direction. So this presentation will show that a viable solution to this problem worthy of global collaboration. So I hope that I do enough of a good job that you want to share this message. And the first slide has my email and cell phone. So do reach out to me. I'm going to walk the conference after to try to see who's interested and make some contact and hopefully be a great success networking globally. All right. So the core of the presentation has 4 parts. So really talk about what's the baseline in 2020. So, and I'll talk about more the meat of the presentation. What is core? Then why essentially core can meet the Paris target and how you can help to make it happen. So yes, I guess I'm really going to say this is all about nothing's going to happen if I stay inside Clair Laser. So I've been outreaching in 2019 and talking to a lot of people for the last decade, 6 years, 4 years. But I'm hoping that this event really is going to be a trigger to outreach at the, at the speed of the internet. All right. Thank you very much for being there, all of you. All right. So the baseline. So the environmental problem are real. See, there's a lot of debate right now between the denial. We all know that. But then so the clean tech. What we've been finding out, and I won't go into that, but Michael Moore, famous documentary, lots of funny work he did. He did the latest work where he does not play much in it, but it's another gentleman in the U.S. which make the planet of the human. We describe essentially the reality that clean tech in many instances are not viable, at least their state and their design may be faulty. And so I don't want to essentially be harsh on other direction, but essentially I'm entering a field where there's a lot of scrutiny already. That's the message, because there's been deception that the net total cost is not viable. Now, the other thing is divestment from hydrocarbon is a problem because of the emphasis into clean tech. People say, well, the oil is but incomplete information from clean tech cause large divestment. So let's pose a risk for the integrity of refined product, for polymer, fuel, and lubricant, because the reality of our world is our dependency on oil is still dominant. All over the planet, 80% of all our energies, especially for the freight and it's 100% for freight and for air transport. And there's only a small, scratching the surface on the car, and the battery is not, and the whole economic of it is just not trivial. And so the real problem is the biggest one is that for a long time we knew that CO2 is increasing, and there's no doubt about this. And there's a lot of documentary show, yes, historically CO2 went up and down, but the rate at which the CO2 are increasing is unknown in all known geological history. So that's why, and then the correlation between CO2 concentration and temperature is very much debate, but we're not going to do that here. The point is the extreme weather event, okay, their frequency and their size are growing, and the latest, storm Laura in Louisiana and Texas is the living proof, in our memory. But the biggest things that's very relevant to 2020 or global reality, which is kind of nice in a sense because it's kind of blowing off a whistle, is that it's been established since 2010. Then global warming, that essentially the climate warming up, increased the frequency of mutation of virus, which is an issue, which essentially jeopardized really. Virus, there's never been any vaccine for virus in known history, so it's kind of a new concept for COVID, but let's not go there. The big point is this COVID and all of its cousins, SARS and MERS, essentially an expression of mixing of viral infection between animal and human, which was historically not thought to be very frequent, and the frequency of those things keep on increasing. So this is an issue because as we damaging ecosystem of many animals, they get sick, their sickness get mixed in virus and get transferred to us. So essentially we all one big pot of living things on the planet, and that's an issue. Now, the biggest thing is there were lots of work. I'm a chemical physicist, so some of my colleagues in the basement in the 80s and 90s were working on ozone problem, and we're calling fondly the 2002 Nobel Prize of Chemical Physics to understand why the ozone was burning. And but now because of the internet, too many information and debate and a lot of mixed information, sometimes really deformation of information. And most importantly, I think the biggest reason, and I'm behind the U.S. and the Chinese right now. China, the decline of support is really, in my point of view, justifiable because while we have target that we know mathematically what's needed to stop the greenhouse gas, we know what's needed We know what's needed to stop the greenhouse gas affect the climate. There is no real viable technology that essentially, there's a lot of claim, but nothing is, if you sit down and nobody have done that, people moving so quickly and panic a little bit that, the reality that we're finding out, and this is the Michael Moore documentary is talking about this, is this, it's not going to work. Many of those things, and many of those biomass, they're actually burning wood, apparently, burning forests, which is back like how they decimated Africa and turned man-made desertification by desperately burn wood for energy, which America is starting to do that. And we have a lot of forests, but it's an issue. So, but we know what's to be done. The question is, we don't know how. All right, so the solution for the necessary greenhouse gases, so expert scientists have established we should reduce man-made emission, called that the Paris target because it was decided in 2015. And in 2018, many scientists and friends were kind of pulling their hair out and say, it's never going to happen because they didn't see any solution in sight, a real solution. There's claim of solution and there's investment, but So our refining process alone is almost the biggest single contributor. And this is the big realization of this presentation here, is that, when you take a barrel of oil, over a third, roughly a third, sometimes a bit less, a little bit more, is burned into energy. So what we find is the best solution, it's found in the problem. And it's often the case, as a scientist, I was trained, when you have a problem, it's kind of almost like the equivalent in the personal life. When people have personal problems, sometimes they run away from them to try to find other solution to replace. But the reality is this: the only viable solution is to take the bull by the horn, as we used to say, and essentially tackle the hard problem. And this is what I'm all about, to work to introduce you to and to show you that there is essentially there's light at the end of the tunnel, but there's going to be a hard, very, 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 very hard job to do. But that's why I say, well, it can only pass. It's really, realistically, it's only feasible if, we can convince many people. Whence my interest to entice you, support your network in China and India and America, whatever you are, and South America and Brazil. Okay, so what is quantum oil refinery? I won't go into fine detail of chemical physics and the fine engineering of this is too much, and Some of it is proprietary, but I just want to give you the big picture today, and hopefully you want to come back and talk more, okay? But in a nutshell, the quantum oil refinery essentially is crude oil refining reinvented with modern knowledge of quantum electronics and chemical physics. Well, that's not unrealistic, knowing the fact that we reinvent, the electron lamp and make transistor and make it so much denser. We reinvent the light bulb, and so many of you in the room here are probably doing phototherapy, and you know that phototherapy only became possible when laser came. That's why it came post-2000. Oh, sure, there was work before with the sun, but this is really quantum electronics and semiconductors and quantum well semiconductors have really enabled both telecom and eventually phototherapy, PBM. So the virtue of drastic efficiency improvement and core, which is this is what those quantum mechanical waves does, that it replaces doing it thermally by doing it just the right energy, okay? So by virtue of drastic efficient improvement, core can yield sufficient greenhouse gas emission, okay? So I did that both by, I don't have a complete core reactor I can sell tomorrow, but I have enough intermediate experiment and calculation in between that I can predict quite confidently that 90% reduction of emission is possible by reinventing our refinery. So this is very exciting, but wait until the end, it's even more exciting. So as a picture here is we're taking lasers and essentially splitting the atoms. Not as simple as that, but conceptually speaking, we think we can do that in vacuum with one molecule isolated, but we're not gonna put oil in vacuum. So the fraction of the crude burn right now when you make fuel, it's about around over the third, 40 to 30%, or depending on the refinery you're working about and the crude you're working about and the catalyst, etc. And if we can improve upon that, if we allow to essentially reinvent that, we can for sure make it 90% reduction of what is, and we don't gonna destroy all this precious crude oil, and we can now convert it into valuable product, polymer, fuel, jet fuel. And we know how to do that, but we're using it all, the energy come from the oil. What I'm proposing to do now is we're going to replace that and doing it better. And I won't go into detail, but I'm going to show a bit where many of you will know about how a oil refinery will work, and I'm going into that. I won't get into how this fully works, but I'm going to tell you that if, typically it's a thermal process in a silo, and then this is 60 feet diameter, there's tons of catalyst, and you vaporize at high temperature the crude, and it goes and it interact with the riser, the crude interact with the catalyst, break down the crude into small bits, and then you distill them. And I won't go into detail of that, but we're going to have to do something similar, but we're not going to use any catalyst. And there is 3 core technology that all, of course, use lasers. So one is conformal heating, which is a way to deposit electrode on very compact, very idiosyncratic shape, so you can essentially make very efficient, compact, and flexible design heating, where you kind of you use quantum mechanics and lasers and material, but you essentially be able to configure in a revolutionary way how you can manage heat, which we will produce electrically now, and then. They're essentially very sophisticated, digitally controlled, automated device to separate the gas with very high precision, which can increase the separation efficacy and precision in terms of vacuum distillation. And then there is this laser heavy cracking, which is essentially a complicated process which enables very precise control of material energy and the mixing and whatnot. So I won't say any more on the detail of it, and we can talk, and I'm glad to consult more on the core. There's a lot to be said, and so it's not a half an hour description, but I just want to give you a flavor. This is very different than normal refinery. So and what core really do and how it's used is when we need to focus. Its purpose is what is of interest. That typically you will have electricity. You replace the power. You make the refinery much more efficient, and you replace the source of energy as opposed to a source of energy going from the thermal combustion of carbon, you replace it with electricity that will drive lasers and very specialized heater and many other motors and process, which part of it already done in current refinery, but it's mostly thermal, as here is going to be mostly electrical and laser. So we have traditional, such as nuclear and hydro and alternative solar and wind. And those alternatives can be multiplexed into, but we don't care what electricity comes from. We have essentially inverter and we have regulated power from wherever they come from. And we effectively use electricity, okay, and we store electricity. When we replace crude with electricity, we're storing electricity and fuel, really, because now petroleum comes from anywhere, and then this is very compact now. So we increase the efficiency, high precision. We replace the FCC process with reduced carbon, and then produce a greener gasoline. So using usual gasoline, diesel, but the difference is this technology is much more configurable. So controlling the product branching ratio, which is the holy grail of chemical physics, and we've been improving with the catalyst, but not nearly as what we can do. We can really shift the curve left and right in centers and revolutionary manner. So this is where the most valuable. Many aspects are highly valuable. One is the fact that you can have much more compact and smaller reactor. You can run a quantum oil refinery on a very small volume of oil, and you can multiplex the unit to have not, and so there's a lot of advantage. So now I'm going to tell you about why essentially Core conserves the mine hydrocarbons. So by optimizing the conversion into valuable product, we can adjust. I blew my thunder again, so this is the information here. We can adjust the product branching ratio to level unheard of before. Okay, so and the relative demand of the output product may change in the future as we switch electrical car and reduce gasoline need. Then we only need more diesel for the freight transportation, or we need jet fuel, and then but normally in the current FCC, you're going to produce a distribution that very kind of little, and you're going to be stuck with excess gasoline. So if you can actually shift the curve as we're going to move toward electrification, that's going to become very handy, because so the global community will still depend on mine hydrocarbon for 1 to 2 decades. That's the reality. And ideally, we're going to want to use hydrocarbon forever, because we're also going to leave polymers. So we need to start to treat it as a very precious, almost like gold in the future. Our grandchildren will use very little hydrocarbon, hopefully, not burn any, hopefully, and they will essentially figure a way to store electricity and to build a battery at the same density or more than we have in fuel. Until we're there, we're going to use fuel for flying and for freight, or natural gas, but compressing it. But compressing gas and aerospace, not there yet. Hence, by making more efficient use of the mine and the carbon, we can reduce crude demand. Because if we can be more efficient by 30%, then if we use the same amount of fuel, then we can use 30% less crude. So, but as we get more efficient as not using crude because we have more electricity, then we're going to use less fuel. So that's going to really help to catalyze the transition toward electrical transportation. So we used to say, before credit card, a penny saved is a penny earned. I mean, I don't know if that makes any sense. Nobody's saving, but a few people, right? I mean, but we say a barrel of oil not burned and refinery heat is one less barrel to mine. I guess that would be a good analogy. So Core usher transition to carbon-free e-transport. So Core Cleantech driving efficiency and transition from oil to electrical transportation. So oil refinery first produce electricity. This is the vision, okay? So the refinery will need to build a lot, will be associated with electricity generation, which is because refinery associated with distribution of gasoline. So now they're going to be associated with distribution of electricity eventually. But first they're going to need electricity. But then because they're already on the distribution of transport energy, it'd be a natural continuity of their business. So what it will do is all the big oil, the old money in America and around the world perhaps, it tends to be against, or they have issue with the, with the newcomer because it's still with their business. So historically, for the last 40 years, for the last for all my past life, I observed nothing but self-destruction. Okay, and now what I'm trying to say is what I'm talking about is so demanding, but so rewarding. I'm just gonna come to reward really soon. That I'm gonna show you that this technology is going to be so rewarding that people want to collaborate because the old money gets their way and the new money gets their way. So the new money will create new technology, electrical and storage and scientists, and the old money will keep on managing their oil, and hopefully we're gonna get a reality check and have the investment community come back to reverse divest and undivest and reinvest in oil because we need cash to do this. This is going to be big. Okay, so essentially both, and so what it's going to do is because you get more efficient, then China won't have to go so far to get their energy, and they're going to be able to exploit everybody all over the planet, like in Madagascar and many places on the planet. There's small oil play, but they're too small to build a harbor to ship the material, and ever too small to thinking building a refinery. But if you have a very compact, very small, unit efficiently converting crude to gasoline, then all of those small play can become worthy of exploitation, which can create a lot of practical new play. I mean, and I think it's going to really help peace in the world because it's going to lower demand for the big play. Okay, like Canada, Venezuela, and other places in Africa, right? And we all know that kind of historically most conflict can be tied to some resources. Oil is often one, so the chance to reduce the probability of future conflict is very much increased. So doing this, I'm going to show you. I'm just blowing my bubble here, but long story short, at the beginning, oil refinery would produce electricity for themselves. As the energy storage would mature, they will switch to a new type of energy provider. So it will allow the transition to electrical transportation because deployment create the necessary large increase in market offer of electrical supply. So essentially, eventually, it's going to energy storage, which is battery. But you know what? We didn't even thought of a smartphone back in the 80s, right? We were taught with Dick Tracy, watch was kind of on the comic strip was kind of a science fiction, and now we all have smartphone and Apple Watch, right? So energy storage battery, we may have something that we can ever. I mean, what's about synthetic fuel? Okay, that is even more dense than gasoline and hopefully environmentally friendly. That's possible if we just open our mind and learning how to do that to have a cleaner and more peaceful society would be, so knowledge is really where we need. So what core is a peace stick? So as a result of improved material conversion efficiencies, we're back into the 70s hippies say, make peace, make war. So as a result of improved material conversion efficiency, core can be an instrument of peace for two reasons. It will reduce the pressure of the rising global demand on crude oil, and two, it will promote cooperation between leading nations for developing market and deploying the solution, and both parties will benefit, from the peace. So we all want peace because if we're in peace, we can collaborate, and because we can collaborate, we're going to develop faster, and develop faster, we're going to get richer. So, this is how society have worked historically, okay? But when people have no imagination and no creativity, sometimes they will essentially want, so my point is this, I want to open a prospect and show it, and I'm open to consult to show it's real, okay? Now, core process. More efficient than traditional refineries. So an upsell on this is a paper result, but this is realistic. Increase efficiency, and I can demonstrate. It's not a 10-minute presentation. Okay, it's an engineering project, but anyway, increase efficiency of material conversion from crude to liquid by 10 to 30%. So we make more material, lubricant, whatever. We make more of the valuable stuff. It's going to be cheaper and faster to build. Right now, a refinery, we find out in Canada, we stopped building refinery. The first one only happened a few years ago in the West, but for 30 years over, almost 40 years, we have no more new refinery. A refinery costs $10 billion. So it's a big project, and it takes 5 years. Now we believe we can start to essentially within 6 months, 3 months, as soon as you have foundation, we can grow organically. And it's going to be way cheaper and organic growth as possible to self-finance by selling the gasoline. So we're going to be able to have smaller player in theory, but maybe the big player will saturate their order book. But the point is going to be a cheaper process, so it's going to lower the risk and facilitate. Okay, so it's going to be much more compact, so you can retrofit another refinery, taking like a tenth, a fifth, or a 20th of an existing refinery, retrofit, making a more efficient outfit and more profitable outfit with less surface, and then you can essentially repurpose the surface. So it's a real estate refinery are big. So there's a real estate play there associated with that, which is of significance, which is going to encourage the old player to hang on to it and associate with new players. So reduce greenhouse gas emission by 4 times 8. So global adoption of core will lower CO2 by 3.65 gigaton by calculation, which is half the Paris target. That's what we need, because by the time we're there and start producing, the parallel development of electrification will essentially start to reduce the emission. Hopefully, right now it's not the trend, but as divestment from oil, from hydrocarbon fuel stop and on-divestment, start to hopefully, right? Then we're going to have a more serious engineering, and we're going to filter, and we're going to essentially the hoax of alternative energy will be cleared up. It's false start, and we're going to get some serious business going on here. So that's my vision. I think it's possible, and I think we need it. And I think most people will agree upon careful scrutiny. And I'm looking to that. And that's lack of scrutiny that essentially brought us, in a very clumsy position right now with COVID and too much denial, the heat and all that stuff. Being responsible has been unpopular, and we need to bring that back and say the truth and know the truth. But, there's too much information, and the good information has been diluted with bad information, and we need to return to essentially being careful who we speak to and look their credential before we listen, and be patient, slow down. So why it's possible to do this within less than 10 years? Here's the thing. Right now, it's been well documented, there's only 700 refineries in the whole planet to produce all the transformed hydrocarbon to produce fuel. So that's an addressable. That's an efficiently addressable global market. There's very few markets so concentrated. Think about it. It's the nature of the beast. Refinery, in order to be efficient, needs to have this economy of scale. And also, thermally speaking, it's a thermal process. It's more efficient if it's bigger. There's a lot of issue with that. It's very expensive and very inefficient too, as such. It's a bit like the steam engine. You can say the old refinery is like the steam engine, and you can say the new core is more like the drive, the efficiency of an electrical, highly efficient lanthanide, magnet kind of electric drive, which is going to be 98% efficient. 95% efficient. So the more compact and efficient solution of core will enable to retrofit existing refinery by using only a fraction. I say that. Initiatives are driven by material energy efficiency improvement, not carbon tax. That's very important to say, because carbon tax has been discussed forever in Canada, at least, in many other countries. And you cannot force goodwill. Things don't happen because you force them. Good things happen because you put competent people, you do a good job, and you do it well. Anything good in automotive, electronic, lasers that came to fruition is done like that. Not by saying do it or else. No, punitive. Intelligent people are not driven by punitive measure. They're driven by reward, and has to be realistic, and you need to know where you're going. There's an organic process of search here. And I guess I'm introducing myself as a leader in that direction, and I hope that we're going to show carbon X is useless. Efficiency, economics, everything that ever happened for real has happened out of real performance. So it's possible to deploy core in the global refining market within a decade. I'm talking to get the point that we have all those 700 out there. Doing so will enable a global market to meet the 2020 Paris targets. A bit late, 10 years later, but better late than never. And if the prediction of the knowledgeable people, knowledgeable for 30 years, are correct, things are going to get much worse before they get better. But it's by the love of our older age and our children and grandchildren, and to be responsible. And this is what we need to do it for, right? I mean, it's going to be hard, but there's no other way to go. Okay, there's no way you can escape that. Okay, because we need to improve this because 80% of the energy still come from there. So it's here's a big driver. It's a $5 trillion market. The chain of supply, the construction business will be, this is the biggest, market ever. This is dwarfing telecom by probably a factor of 50, 20. Makes sense, right? Big stuff that moves is more expensive than small stuff. And construction has always been bigger than electronic all put together, right? So core is disruptive, a $5 trillion technology market offering better refining performance. It's guided by cable, mechanical, and chemical engineer. Core can scale to in less than 10 years. I mean, scaling means taking over and replacing the old stuff with the new stuff. Nobody much use essentially a flipper anymore because, smartphones scale to replace the flipper. It took 5 years. Well, it's small. It's easy to produce. This is a bit bigger. But it's feasible. So core deployment is practical because improve ROI for crude oil. Essentially, the customer wants it, the supplier wants it, and the people need it. So hopefully government will wake up and support it. So market forcing innovation, but I think government should be out of the way. They should learn to be, when they get, as I like the saying of Reagan says, government don't solve problems, they subsidize them. Meaning, sometimes by avoid doing the right hard job, they prevent evolution by patching and handicapping more than helping in many instances. Many thinkers have shown that's true, and that's a philosophy partly. So why is core can do Paris? But there's double realization right now, and I guess it's going to be obvious. Double realization bring us at the edge of despair or breakthrough, depend on character, right? We still have a major dependency on carbon, yet depletion is happening. So those things are true. We depend on it. We know that. Depletion is happening. Well, big oil is not singing the song just yet. But it's important to do because that will give value to the oil only if we have a transition to replace it, right? So climate change are real, but alternative right now, as they are not ready to replace oil at all. That's why they're stuck at 20 and the battery won't scale to the freight or the boat. So what we shall do to give up, I said, not on my watch. So I said, summary of realization, just summarize where we are right now. With change upon us, depletion is being obvious. We depend on crude oil to maintain our way of life. Dependency on polymer pressure preserve resource. We do need to have polymer for a long time. We need to preserve hydrocarbon. That needs to be and that people start to say that. If you search, you're going to see people have said that. Energy storage will be among the challenge. This is where the hottest things. Maybe battery is good, but maybe battery is not the ultimate limit. That's my intuition. My knowledge says so, and I can see a view to replace something. So climate change problem, size of the storm, frequency of viral mutation, this is the consequence of the underlying emission. And this is becoming clear by whoever wants to find out. The scientists who need often a very, very dim voice about those, but this is a very unspoken truth that essentially, we had this dialogue, maybe in the newspaper, some people blame the Chinese, some people blame the American. But the reality is everybody of us who's burning oil is responsible because if it's the climate change, and the climate change is real, right? There's the climate change, and we are responsible, so we should all pitch in, right? Stop blaming, roll the sleeve, get to work, okay? And that's going to be a rewarding work. We're going to create the new era of clean tech that's going to engage everybody, reward everybody, but it needs to be orchestrated properly, okay? And we need to stop, I know this IEEE standard type global, the German, the American, hopefully the Chinese, opening up transparency and having common standard is going to be crucial. So Chinese will have to be more, open up to stuff, and I think they are. I am not in the secret of the God here. I'm just a small player in Kitchener, Ontario, but, I heard from the newspaper that sometimes people discuss. So we have to open transparency on both sides of the Atlantic. Okay, so what I'm trying to say here is that a unifying force. So essentially, between the rival, there's two types of rival. There's the traditional conservative, big oil, old money, and there's the new money, new tech. Try to sometimes create fear to sell the insurance, or blah blah blah. But what I'm talking about is really we need to get the best on both sides and work together. to slow down greenhouse gas emission. It's a daunting yet uncommon challenge. And I think this technology can do that. Also, because it's so big and there's so much reward and you cannot go fast enough, first we need to all figure out what works. Okay? So intelligence in China and America and Canada and Germany and every country where in Northern Europe, everywhere there is intelligence, we should network and make committee and essentially figuring out, agree on that, what is the problem and breaking down the problem and sharing the information of the solutions we found and agree to essentially royalty-free global knowledge of quantum well refining solutions, and then trading to each other, specializing to each other, and building solution so that we can unite, because we cannot have enough people working and doing it bang up. It's a refinery, it's a high energy concentration. You cannot screw that up. So a lot of work and developing, optimizing, engineering, qualification, safety needs to be done fast. So in order to do a good job, we need to work as a team. Okay, and so we first need to come together, go back to work, and come back together often on a monthly basis, and really, reinvent our refinery. Okay, and to slow down. But we need to have the left and the right, and America and everywhere else, and we need to have different big nations, America and China, to really talk to each other. Right, the smaller country already talk more easily, but we need to orchestrate that. I think this is one of the communications always a problem. Okay. So core create a huge opportunity for unifying force between traditional rival, but a huge gain, a $5 trillion market with cleaner oil tech to help transition to e-transport. This is like, I don't think there's a better technological, business, and philosophical reason to work hard in business. Okay, so core is designed to be a flexible technology capable to control product branching ratio for transforming crude oil into product that we need, and we're gonna need less fuel and more lubricant as we're gonna have more electrical, right? So, and at that point, I want to say the whole world, because of Japan tsunami, have been in fear of nuclear, and Canada has historically, and China knows that because China, my friend in nuclear energy told me that Canada sold a few nuclear reactors to China, and they really carry on the tradition, and now they have maybe a dozen of them or more. So China knows nuclear is important, and they're growing there. France knows, the developed nation knows, but for whatever Germany, and then we've been essentially, shutting down the nuclear, so it's very, very bad that we've been so hard on the nuclear shrinking. So what happened is this. So we know that nuclear, if you know here, we know that nuclear existing on the Earth's surface is a reference, and here it shows that people have found out since many years that there is actually naturally occurring nuclear reactor, and it stands to reason that in the core of the Earth there's enough density concentration of gravity to have like heavy element, and maybe some of the heat of the volcano will make us a warm planet. Nobody went down there except Jules Verne's imagination. But, chances are we do have a nuclear reactor down there. But if we have some at the surface, it stands to reason there's some down there. So the reviving nuclear, Canada had produced the most safest heavy water, moderated nuclear reactor in 1967 or 63.
Dennis.
Okay.
Hey, Dennis. You have another 5 minutes to. Yeah.
Okay, let me wrap it up. So long story short, Canada has been a leader. So but bad politics. We need to revive nuclear energy is very important. So any serious plan to identification of any country cannot discount nuclear. Nuclear can be very safe. And again, nuclear development accelerate and peak in the 50s and the 60s. Since then, with computer, with quantum mechanics, with essentially what computer can do, we created lasers. We can reinvent our refinery. But that's another story. Okay. But my point is this: chances are that if we're going to let go oil and we need electricity, and there's limit to how much we can do on hydroelectric, nuclear is an absolute necessity. And I'm sure India and China knows that, but Canada doesn't seem to wake up to this, and America is working on it. So legacy of Vannevar Bush. Long story, I'm talking for Canada here. We need to align the funding because academic is a bit too much freedom and they do whatever they want. They need to essentially to be given, funding driven by the need. And when we're in a crisis, at least for a decade, we're going to need to change because often they work on useless, they're kind of interesting and maybe in 25 years maybe, but most of the stuff going nowhere. and it's based on ego more than need. So we need to align academic in Canada and the US and developed countries to have critical mass effort. Nothing is done in China, and it's been doing it in America for a long time. So what I'm asking you now is how you can help to make it happen. Spread the word, tell your friend, reach out, promote, propagate the outreach effort, help us disseminate the hope and reverse negative trend. Because, desperation and, false clean tech that like some of them, I won't name, but some of them are hoax. It's obvious. If you're a physicist and you can calculate, you say there's no way. I mean, I don't see it. I don't see how. Reach out and send us a list of contact who are interested to receive our information, specify corporate or domestic, and reach out to elected officials. So, we like to reach out to Bill Gates, Elon Musk, and Jeff Bezos. Those people are busy. If you know how to get noticed, to get vetting process, to pitch competition, those people, share that with me because I'm a nerd. And when all you have is a hammer, everything looks like a nail. So I'm always developing. I love to develop. And, I do some marketing and I survive and I thrive at time. But I could use some help to reach out where the big money is, And so if you have a hint, please share that with me. All right. So core oil refinery. So core is a petrochemistry in the era of depletion. It's strong. It's a support for long-term energy security, improve efficiency, promote transition to the clean energy, electrical transportation. So finally, I want to say thank you to Richard Marceau, who passed away a few years ago, but he was a great inspiration. He's an amazing overachiever that wrote 2 amazing books. If you want to know about Canada, those are on the web for free. Those are amazing, inspirational writing that as a small nation, how Canada have essentially leveraged its resource, and we're on the up and up really rapidly up to the early 2000s until thing happened. So essentially read him, and I'm grateful to him because he encouraged me in the first few years to carry on. I had a chance to meet with him a few times in his busy life. So I'm very grateful for that. And so that's it. So I'm done with the. So what should I do now, Mister? Should I go back to the? I think I should go back.
No. Thank you for the great presentation. Now we will be open for some questions.
Okay. Oh hi. So I hope. Sorry, I'm overstaying my welcome. I realize. I apologize for that. Hi, Rachel.
Hi, how are you? Nice to meet you.
Are you in Brazil or you in Europe? Yeah. In Brazil?
Yes, in Navdeja University.
Oh, yeah. I think I saw your abstract. I read a lot of them, so I didn't memorize all of them.
Yeah. We have many students participating in the meeting.
Yeah, it looks like you're dominating the present. That's good. That's good.
Yeah, really good. I think I'm checking here. I think we have one question. I think it's Harshit. The person is requesting you please give 2 or 3 more impacts that core can have apart from climate change. I think this is the question here they post.
Can you repeat it succinctly?
Yes. Your presentation is thought-provoking. I would request you to please give 2 or 3 major impacts that core can have apart from climate change.
Okay, so you're asking for 3 how core can
can have apart from climate change.
Oh yes, yeah. Well, the 3 ways is number 1 is by essentially reducing emission upon deployment by reducing the greenhouse gas emission. That's number 1. Number 2, by helping the transition from oil-based fuel transportation to electrical transportation. That's number 2. And number 3 is, I believe, is that by enabling exploitation of smaller oil play, which is often deemed unexploitable because, as I say, like in Madagascar or some place like that, they're too small to even build a harbor to boat the crude somewhere else to be refined, let alone to build a refinery there. Forget about it, right? So by having something that's very scalable, we can make an efficient, the process being efficient at a small scale, and it's scaled up to multiplexing. That's what enabled the speed. So you can build, when most houses traditionally are built on site and it takes 3 months, whatever. But there is a type of construction where you prefab the house, and all people do here is they will build the basement, and then they'll come and drop the house in 6 hours, and then your house arrives. So the like thing is like a prefab oil refinery cork technology. You come and you have module 1, module 2, module 3, and then you want 5 sets of module, and you can essentially, because it's modular, you can make it much smaller, but the efficiency is already maximized at the small level. So therefore, you can exploit small play. So you don't have, because whenever you transport the oil, like in Canada, we make crude oil in Alberta, but when we're piping it down all the way across North America to Cushing, Alberta, don't think this thing goes by itself. You consume an insane amount of energy to pipe a viscous fluid through the pipeline to have the continent. Then you have some time to use dilbit. It's very energy intensive. So the net transportation of fuel is not factored in, but if you factor transportation, sometimes you only have, a quarter of the crude at destination. So now if you can refine it on site and prepare the fuel, is the reduction there, it's something that's unthinkable. That nobody can consider it even possible, but is now made possible. Same thing with electrical transportation. If we find a way to make synthetic fuel, battery become obsolete. Battery have been the bottleneck of electrification for transportation. So what about if we start to, if people understand the physics and engineering of a core, they will see like me that the concept of making synthetic fuel is very possible, right? So anyway, so that's the 3 ways, reduce emission,
Perfect.
facilitating conversion, and access to new play, which reduce the cost and the energy and the emission associated. When you transport natural gas from America to China, that's a lot of oil burn, or natural gas burn on shipping transportation. If you don't have to do that, then you can get something locally, and that's so much better, right? I'm just saying.
Yes, exactly. Thank you so much. Any more questions? Thank you so much. Thank you so much.
Oh, thank you, Rachel or Raquel?
Raquel.
Thank you,
Yes.
Raquel. Raquel, oh, thank you. Sorry, thank you,
so
Raquel.
much.
Thank you so
Wonderful
much.
presentation.
You're welcome. So where do I go next?
Thank you,
I'm gonna click. Where do I go next? I'm gonna go to lounge or lobby or what?
I think we go to backstage.
No, let me move all of you to the next
Okay, so I'm
session.
gonna go to backstage now?
No. You will be a listener now. Yes, you will
Everyone,
be on the floor.
I'm so sorry because my computer has
so
some
it's
problem.
happened by itself, or do I go
start
somewhere?
my presentation. My topic is laser cooling in turbine double-yacht crystal. My name is Biao Song, and I come from East China Normal University. The outline includes the following parts. Firstly, the motivation and the basic principle on laser cooling stories, the recent progress of laser cooling rare earth doped materials, and the laser cooling turbine double-yacht crystal, and the last is the outlook. Okay, in 1929, Peter proposed the condensed materials can be cooled by light. The basic concept is the material absorb the low energy photons from the light and excite from the ground state to the excited state. After that, thermalization and decay to the ground state eject the high energy photons. The difference energy come from the hoist. So this process repeat many times, and the heat in the heat of the hoist can be removed. But some researchers argue this concept because they think this concept avoid the second law of thermodynamics. London introduced the concept of the radiant entropy and the radiant temperature to solve this argument. The anti-Stokes furnace cooling can be used to optical refrigerator. Optical refrigerator have the following advantages, like no vibrations, compactness, no moving parts or fluids, high reliability, no need for cryogenic fluids. So we can use the optical refrigerator to the IR detector, steel conductor, and biotechnology, and integrate circuit. Also, we can use to the radiation balance laser. Thermal management and regulation are the key to achieving high-brightness solid-state lasers. Look at this picture. These four-level models describe the optical pumped layer stopped laser. This process is the Stokes furnace process, and during this process, the hoist will become heater. When the hoist become heater, it will lead into thermal quenching and thermal stretching and thermal lacing. For ideal laser, we can see in this picture the relationship of the power of laser and the power of pump source, like the dashed line, but in fact we can see the powerful laser like this. We need to some management and regulation to achieving high brightness solid state laser. If one can calculation the anti-Stokes fluorescence cooling and the laser process, they can achieve the radiation balance lasers. The heat from the laser process, we show here is the laser process, and will produce the heat. Describe this equation, and this process is the anti-Stokes fluorescence cooling process, and will remove the heat from the hoist. And can, as described in this equation, the total heat can be less than zero if we compilation the anti-Stokes fluorescence cooling and laser process. This picture describes the history of laser cooling flare stopped materials. In 1995, Richard Epstein realized the laser cooling solids in the turbine-doped the blend, and the best decode of the turbine-doped the blend glasses is 208 Kelvin. After that, Manson Shegebeher used the turbine-doped YLF crystal and make the record temperature is now the 87 Kelvin. Our group, we use the turbine-doped LLF crystal for laser cooling solids, and now we obtain the cooling temperature of this crystal is about 142 Kelvin. After that, we study the turbine-doped crystal. Why we study this crystal? Because this crystal can be used to high power laser. At the same time, this crystal have the good properties for laser cooling. Okay, let me introduce the principle of laser cooling solids more detail. For simply, we use the four level model. The ions, the ions in the ground state, state 1 can be pumped by laser to the excited state 2 and excited state 3. When the ions excited to the state 2 and then can thermalization to state 3. After that, the ions in the excited state can go to the state 1 and state 0 via radiation. However, the ions in the excited state 2 and excited state 3 can also decay to state 1 and state 0 via non-radiation, but the probability is very small. So the influence can of the non-radiation can be ignored. Okay, the physics problem, the physics process can be described this radiation. From this equation, we can obtain the cooling efficiency of the materials. The parameters affect the solid cooling property include the cooling efficiency described as this equation. This is the external quantum efficiency, and this is the efficiency the resonant absorption efficiency. This is the frequency of the fluorescence. This is the frequency of the pump laser. The parameters affect the solid cooling also include the heat load from the environment. Include the heat from the radiation and the airflow and the fiber contact. The thirdly parameters are the observed power laser. So we needed to minimize the heat load and enhance the absorbed power of laser. The absorbed power laser of the material to obtain the lowest temperature of the material. Let's look at the Yark crystal properties. The ytterbium doped Yark crystal have the features like this: the wide absorption bandwidth, low lasing shear hold, high slope efficiency, large luminous cross section, linearly polarized emission, and single mode. So this crystal can be applied to the high output power laser, and also can be applied to the optical refrigerator. Okay, let's look at the absorption and fluorescence spectrum of the ytterbium doped Yark crystal at the room temperature. The blue line is the absorption spectrum. The red line is the fluorescence spectrum. The dashed line means the mean average fluorescence wavelength. The blue area is the cooling tile. It means the pump wavelength must be within this area for laser cooling. the insert is the energy level of the turbine in the yard. This is our experiment setup. The pump source, my pump source is the fiber laser. The wavelength of the fiber laser can be tuned from 1018 nanometer to 1080 nanometer. And the highest power is about 440 watt. The laser injected from the fiber laser and into the vacuum chamber. The crystal in the vacuum chamber, and the fluorescence spectrum is collected by the fiber into the spectrometer, and the temperature of the crystal is nominated by the computer. This is the scheme of our experiment. The figure B shows the results when we pump the crystal. Use the laser at the wavelength 1030 nanometer, and the other wavelength is the 1049 nanometer. We can see from the picture, the lowest temperature of the crystal is about 225 Kelvin. The figure C shows the temperature of the crystal change with time. We can see from the picture when after 20 minutes or 8 minutes later, the temperature of the crystal changes small or have no change. Based on our experiment, we use the equation mentioned before, fitting the experimental results. We can obtain the external quantum efficiency and the background absorption efficiency of this crystal, and we find the global minimal achievable temperature is about 180 Kelvin from the cooling windows. If we reduce the background absorption efficiency to this one, and we find this crystal can the global minimal achievable temperature of this sample is about 135 Kelvin. So we find the ytterbium doped Yag crystal have the great potential for laser cooling and for radiation balance laser. So our next work is to utilize the cavity to enhancement absorption of the pump laser and increase the higher doping level. All we call layer stopped Yag crystal for laser cooling and for radiation balance laser. Okay, the conclusion of our work, and with the temperature of the 3% ytterbium doped Yag can be cooled down to 225 Kelvin in vacuum, and we demonstrate ytterbium doped Yag crystal is the promising candidate for IBLs. The current system is suitable test bed for sample evaluation. Here we thanks to the Mauro Tonelli Pisa University and Yangzhou Wenjingwei and Mason University of New Mexico advice for the experiment. Okay. This is my work. Thanks for attention. Welcome to East China University in Shanghai, and welcome to our lab. Thank you.
Thank you for your presentation, Professor Zong. Now we are open for questions. I would like to remind you that you can also use the icon on the side to make your questions, the icon Q&A. Any questions? Thank you so much, Professor Zong, for your presentation.